Some of the identities today, I think, have like double angle stuff in them, and I think one or two don't. But so it'll be good practice. And if you think you know how to solve it, I would say go ahead and get started. You don't want to just wait and watch me do it. That's not going to help very much. That being said, I'm gonna get this one ready to go, and I'm going to ask you, what do you notice? What jumps out at you? What strategies are you thinking? What are the strategies? What strategies do you think might work in this case? That sort of thing.
First, change everything to sign, or just to sign.
Okay, so right, so there's a cosecant on both sides. Very nice. Good to notice. Not going to be easy to work that way. We don't have formulas for cosecant. Yep. Yeah, why double angle? Because there's a double angle on the left side. If there's a double angle, that will never be equal to something that's not a double angle. Cosine of 2 theta will never be equal to like cosine of theta. The relationship is the formulas that we saw yesterday. So like if you see double angles on both sides, well, that might be different. You probably wouldn't, but if you did, that might be different. But if there's a double angle on one side and not on the other, which would be likely, like that has to be resolved, right? Because you've got to have the same thing on both sides. So 100% we're thinking we're going to use the double angle formula somewhere. Okay, so let's get started. I can see that what I'm going to do on the right side is going to be quick, so I'm going to do sort of 2 lines, and I'm going to do them slowly so that you can see what I'm doing and you can think it through and make sure that you can follow it. So this is like cosecant theta times what? Nice, 1 over 2 cos theta, which is 1 over sine theta times 1 over 2 cos theta, which is what? 2 sine theta cos theta. What does that look like? Identities are a lot about noticing things. Oh, this looks like something I'm familiar with. Yeah, very nice. If you didn't notice that, you might be stuck. You don't have much choice on the left side anyway, but if you didn't notice that, then it might be tricky to finish off this question. But if you do, this is 1 over sine of 2 theta. And again, even if you didn't notice, which at this point you should because they're basically the same, but even if you didn't notice, like we have to do something with that double angle. Have to. So we've got theta on one side and 2 theta on the other. Remember, you can't just do this. Sine 2 theta does not equal 2 sine theta. Like it's not just that. Yesterday we were using the formulas, now we're doing identities. Sometimes that's enough for people to start making silly mistakes like this. So it's still not just equal to that. We talked about the difference between horizontal stretch compression and a vertical stretch compression. So I'm going to use the formula, and even if I had to look it up, I'd be like, oh, right, of course. Awesome. Kind of a simple one, but a couple of nice little details in there, and just really thinking about observing when you have a double angle that at some point you need to do something with that. I'm going to give you a minute to think about this one and see if you can come up with something. I'll give you the tip that there's lots of different little ways that you could do this. And I think people see it differently, so I want you to try. What would you do? What do you notice? First step to identities is observation. So what do you notice? Blake, what do you notice here? Anything? Like, right or wrong, helpful or not, that's not the point. What do you notice? Cosines, good. Why? Why? Yeah, like, do you mean, like, have you already done it? You know that's going to help us? Okay, very good. Why do we know that we can use the Pythagorean identity? Like, why is that something to think about? Okay, nice. What else? Sine squared. Like, I see squareds. Like, that's a small observation, but I think that's an important one. I see squareds. No squareds in that one. Like, it's different. Right? So it puts you in a different, maybe, mindset. This one has reciprocals. We're doing it one way. This one has squareds. We're maybe going to do something else. I see squareds. I start thinking about Pythagorean identity immediately. Very good. What else do you notice? Anything else? That's enough, because you can solve it just like that. But Asia, do you have your hand up? How would I do that? That's an interesting idea. I can turn 3 cos squared into cos squared plus cos squared plus cos squared. It's like 3x, which is x plus x plus x. You don't have, like I said, there's lots of different ways to do this question. You don't have to do that, but that could be helpful. And that's an interesting thing, like technique that you could take advantage of sometimes. Nice. That's another, can be a very useful observation. On the left is only cosines, on the right is sine. So what could I do? So 3 cos squared x plus 1 minus cos squared x minus 1. Thank you, very good. And then what happens?
The 1's will cancel each other out, and then 3 cos squared x minus cos squared x is just 2.
Yeah, so this is good. This is 1 minus 1, which is 0, and 3 of something minus 1 of something is 2 of that same something. We're done. But I want to show you, you don't have to write all these ways down, but just watch. What if I had split it up like Asia suggested? I'm going to just do it this way. 2 cos squared x plus 1 more cos squared x plus sine squared x minus 1. Now what does it look like? What's cos squared x plus sine squared x? 1. So this is 2. Like, it's really all the same thing, right? But it's just interesting how slightly different observations give us different answers. Or we could have changed the 1. I've seen people do this. Change the 1. Now this is tricky because you can change the 1 into a lot of things. You might do this if you look ahead, like a game of chess. You're playing 8 moves ahead or something, and you might see that this works, and you might do it this way, right? So I could do 3 cos squared x plus sine squared x minus 1. But I'm going to write 1 in a convenient way. That is sine squared x minus cos squared x. and I get 3 cos squared x plus sine squared x minus sine squared x. So that's how I'm going to get rid of it. Plus, nope, minus. That should be plus, sorry, because that needs to be minus cos squared x. And those guys are gone. And the 3 minus the 1, we get the same thing, 2. Small different things, but it's interesting. Like everybody will see it a little bit differently. Yeah.
So I did it a little bit. It's similar to the first one, but I changed it so that the sine squared x minus 1 became negative cos squared x. So would that count marks?
Ooh. If I like that. If I were to do it that way, I would add this step. If you didn't follow that, just it would look like this: 3 cos squared x plus sine squared x minus 1. I would factor out the negative 1 first just to be sure. So minus bracket 1 minus, like that. I would show that step just to be sure that whoever's looking at it knows that's what I did. Yeah. That's an awesome little idea too. Switching negatives from one term to another by factoring. That can be a useful technique. Okay, again, I want you to give this one a shot. If you're still on a bit of a stage where you're hesitant to start because you're not really sure if what you're thinking is right, you have got to just start diving into these things. You've got to think about those strategies. Like I would write them down. In fact, you might make your own cheat sheet. I can show you an example in a minute. That where you write down the identities that you're allowed to use, you write down the strategies, you write down some of the other things that we've gone through, like all the new formulas and the cofunction identity, even odd symmetry. Like you could write all that down in a central place. Okay, that might be a good idea, and then start explicitly looking at the strategies, reading them over, and just trying one. This is to me, this is an example of one where it may not be obvious how to get started, but if I use the strategies and just have faith in them and that idea of observation, it works out really simply. So what was your first step for this one, Jason?
Change the secant into one of our codes.
And then you were finished on the left side and you moved to the right? Very nice. And what do we do on the right side?
I replace the sine 2x with the equation for it, so 2 sine theta equals
And why'd you do that?
because we need the cos in general.
That's neat. We needed to get a cos on the bottom, and that'll do it for us. That's good. What else?
There's no double angle on the left side.
Yeah, like that double angles, we've got to turn it into a single angle for sure, right? And it turns out that even if you didn't see it, That is absolutely what solves this, because then I get 2 sine x over 2 sine x, and this is just 1 over cos. Okay? Any questions? I think there's a couple more little things that we're going to do, but they're a little bit different. So those are all the identities we're going to, actually there is one more that we're going to look at. But. So the instructions here are a little bit different. Prove the following is not an identity. Why might somebody think this is an identity?
Well, someone might think because sine 2 theta goes into 2 sine theta cos theta, that sine 3 theta would work the same.
Right. And then you might start to think, I wonder if it's true for all numbers. For, like, sine 4 theta is 4 sine theta cos theta. Sine 5 theta is, and turns out it's not true for 3. So, don't make up your own formulas. The ones we've used in class are the only ones that we're allowed to use, the only ones that work. Making them up is not going to work. But a neat way to think about identities and understand them is, how could you prove something's not an identity? Does anybody have thoughts about that?
You could choose what you want theta to be, and then just send it into both sides, and it should come out as like different answer for both sides.
Yeah, good. So if you think about what is an identity, the definition of an identity is a statement that's true for all values of the variable, assuming there's a variable in there. This is an identity, but not a very interesting one. This is an identity, but again, and sort of one that you use. Like every time you actually add 2 numbers together, you're kind of using an identity. I take 5 plus 5 and I replace it with 10. I've used an identity, right? But we don't think of it that way, but it's true. But the identities we talk about are the ones with variables. So for all values of theta, is the left side and right side equal? Another way of thinking about that we did the other day, graph both sides. Graph the left side separately from the right side. Are they the same graph? Like we talked about that yesterday a little bit, right? We're not going to do that here, but that's the idea of an identity. So to add on to what Emma said, what's interesting though is it could be true for some values, right? Like 2 graphs may cross or they may not. I could graph a sign here and a sign here and they'll never cross. Or I could graph another one like this and they'll cross here and there. So if I pick a value for theta and it works out, that doesn't mean it's an identity. It just means that you happen to pick a point where they happen to be equal. So how do you avoid that?
You just simplify them to a point where they're like 2 things that just can't be equal. So like sine 3 theta equals sine 2 theta.
That's an interesting idea, that you could try to simplify it to a point where you can see where they're not true. I could also pick values that I wouldn't expect them. Like, for that matter, I could say, well, what if theta equals 1.33587? What are the odds that they would be equal there? That would be insane. But usually we pick things in terms of pi, but you could do that. But would I pick pi by 4? Probably not. I mean, this has transformations, but still sine and cos are the same for pi by 4, so I probably wouldn't pick pi by 4. You could pick pi, you could pick pi by 2, 2 pi, you could pick 0 and see what happens. But just be careful that if you pick those like type of values, you may get that they're equal. So go ahead and pick your own value, give it a try. You don't have to do exact value here, you're just plugging it into your calculator. You can pick anything.
Apparently they are equal at 6.258.
Oh, really? Oops. So I tried pi by 2, and on the left side I got -1, on the right side I got 0, so there you go. All it takes is one value. I also tried pi, and sine of pi is 0. Sine of 3 pi was 0, so it actually gave me 0 on both sides. So that didn't work. So that's what I mean by be careful of what you pick. But if you ever got a question like this on a test, I'm not trying to trick you that it is an identity or something weird like that. So you would just have to keep going until you find one. Okay, fairly straightforward. It's just a good little thinking activity. And here's another one that is an interesting little idea. We won't do much of it, but use technology to graph 1 minus tan squared x over 1 plus tan squared x and make a conjecture about another expression that is equivalent to this expression, then prove your conjecture. So I'm going to graph it for us, and I want you to look at it. 1 minus tan squared, tan of x squared, I hope that's how you type it, divided by 1 minus tan of x squared.
You have 1.10.
Thank you. It's supposed to be minus. That, didn't work. That's supposed to be plus on the bottom, that's why. There we go. Ooh. I'm going to give you a minute to see if you can think about what that is. Make a conjecture about what the expression is, and then prove your conjecture. In other words, whatever that graph is would be, the equation of that would be an identity with that statement. It'd be equal. It'd be an identity. Does anybody have any thoughts on what that graph is? What do you think? Cos 2 theta. Very nice. So I would use cosine, like it could be sine with a shift, but why would we do that? So I would use cosine, and instead of a period of 2 pi, it's got a period of pi. So the period's been cut in half, which means you have a horizontal compression, which means your k value would be 2. Very nice. How many people were thinking along those lines? That's a skill from the previous unit. They don't go away. You know what I mean? That's something we should be able to do, is look at a graph. But it can be hard out of context. I wouldn't have expected everybody to be able to just do that. So here's what I have. Therefore, 1 minus tan squared theta over 1 plus tan squared theta equals, with a question mark, that's what that is, cos 2x Are they the same? And I set it up. So I'm going to let you try this one as more identity practice. I will put the solution up after, but I'm going to let you work away at it, and then you still got 20 minutes where you can work away at other practice. Okay?